Good morning, everyone, and welcome to my presentation on Hilbert's 10th problem. For anyone not familiar with how I do presentations, because my voice can be a bit difficult to understand, I take the liberty of pre-recording them so you will actually be able to understand a word that comes out of my mouth. With out of the way, let's begin. So, what's this presentation actually about? Well, we'll be looking into how Hilbert's 10th problem was resolved. Shocking, I know. First, we'll cover some basic background information, stuff like what the problem says, how Davenport equations work. This is all stuff we're 99.9% familiar with, so feel free to pull out your phone and do something else while I talk about it. More importantly, afterwards we'll be working through the paper by Davis, Putnam, and Robinson. This paper, while it did not solve Hilbert's 10th problem, proved a critical result, which, when combined with the work of Matisevich in his 1970 paper, completed the solution of the problem. Now, I will warn you in advance, the entire second half of this presentation is about Matisevich's number theoretic results. In fact, even though this is technically a computability presentation, as I was writing this, it just ended up gravitating towards the number theoretic side of the solution. So, my apologies in advance. Now, let's get those basics out of the way. I could begin with some history about Hilbert and the problem, but I'm not going to do that. I should spend 10 minutes talking about who Hilbert was, what he did, why we care about him, why we care about the 10th problem, and so on and so forth. I should even spend time ranting about why he should be referred to as a Prussian instead of a German. But this would all be misery for you, because we are already familiar with almost all of this. So, with that in mind, let's talk about the question proper. It states, entscheidende Losbarkeit einer der phantastischen Gleichung, einer der phantastischen Gleichung mit irgendwelchen unbekannten. Yeah, I can already tell that my German pronunciation is terrible. More importantly, I don't think anyone in this room speaks German, so let's look at it in English instead. Determination of the solvability of a Diophantine equation. Given a Diophantine equation with any number of the unknown quantities and with rational interval numerical coefficients, to devise a process according to which it can be determined by a finite number of operations whether the equation is solvable in rational numbers. What could that even mean? I mean, seriously, rational integers? Isn't that a tautology, practically? Let's unpack it into modern English. By a rational integer, we just mean an integer. Apparently that was what the Germans called integers at the time. by a process according to which it can be determined by a finite number of operations. We just read an algorithm. Again, apparently that's just the phrasing at the time. Putting that all together, we get the following. Hilbert's 10th problem. Find an algorithm that, when given a Diophantine equation P with integral coefficients, determines if P has a solution. Quite a bit shorter, I must say. Before we continue on, let's make sure we're all on the same page. As I'm sure we all know, a Diophantine equation is a polynomial equation in which only solutions over S are sought, where S may be the integers, the naturals, or the positives. Technically, it should only be one of these, but different papers use different conventions. I mean, after all, Hilbert was interested in S equals Z. Thankfully, it's easy to see that a solution for one yields a solution for all. We prove this fairly simply. For the integers to the naturals, you use Lagrange's four-square theorem. For the naturals to the positives, just add 1 to each variable. And for the positives to the integers, systematically check for every solution to be positive, negative, or 0. It's very cumbersome and exponential time, but it's computable. With this in mind, we'll take S to be positive, although that's really not going to make an appearance throughout this entire presentation. Now, this definition is a bit less well known, but I'm sure you can figure it out based off of the name. An exponential Diophantine equation is an equation which can be put in the form EX equals FX, where E and F are functions built from X and the positive integers by addition, multiplication, and exponentiation, in which only solutions over the positives are sought. That's a bit cumbersome, and thankfully it can be simplified. Every exponential Diophantine equation is equivalent to an equation EX equals 0, where E is a linear combination of products of terms of the form alpha to the beta, where alpha and beta are either variables or particular positive integers. Proving this is fairly straightforward. It relies on the fact that if you have two systems of equations A equals B, then this is equivalent to an entire single equation, sum of the quantity AI minus BI, quantity squared, equals 0. Now, we just need one more definition out of the way. A set S is Diophantine, respectively exponentially Diophantine, if there is an E of Sx, where S element of S, if and only if there exists an X such that E of Sx equals 0, and E of Sx equals 0 is Diophantine, respectively exponentially Diophantine. With this, we're ready to begin the papers proper. Now, if you took my advice and zoned out for that last section, I highly recommend you pay attention to this one. Now we're going to look at DPR's results. Their work roughly falls into two parts. In the first, we encode recursive linear model sets as polynomials. This is mostly work by Davis. Next, we transform those encodings to exponentially diaphantine sets. The encoding that we're referring to for recursively enumerable sets is called Davis normal form. This encoding was developed for Davis's doctoral thesis. It reads as follows. For any recursively enumerable set S, there is a polynomial P of x, y, k, z, such that x only of S, if and only if there exists a y, such that for all k less than or equal to y, there exists a z less than or equal to y, such that p of x, y, k, z equals 0. Here, p has integral coefficients. Moreover, the z less than or equal to y restriction is sometimes dropped. They are easily seen to be equivalent. We'll often abbreviate this to say x only of S if and only if there exists a y, such that for all k less than or equal to y, p prime of x, y, k. We call such p prime and other similar predicates diaphantine predicates. Now, to prove Davis normal form, we will proceed as in Davis's computability and unsolvability. Now, I will apologize in advance for the nature of this proof. The book is from the 50s. It's written in a slightly bizarre manner, and as a result, a lot of the proof was somewhat convoluted, including a high number of references. I've done my best to recreate it, but it can still be a bit annoying at times. What's supposed to be what Davis calls a combinatorial system. What he means by this is a formal grammar. Basically, he concerns himself entirely with Turing machines operating on words instead of URMs operating on numbers. So this is a slight nuisance we have to deal with. If a word W is produced by a combinatorial system gamma, we write Turing cell gamma W or gamma proofs W. Fairly simple to see why we do so. Moreover, we define the set of integers generated by gamma to be the set of all n such that gamma proves 1 repeated n plus 1 times. So now at least we can work with integers as usual. From here, it's helpful to restrict to a more specific grammar, which he calls a normal system. This is a combinatorial system with alphabet A1 to AN, as well as duplicated versions of these. In production rules, AIP maps to PA prime I, A prime IP maps to PAI, and GIP maps to G bar I prime. Here, GI and G bar I are words in the alphabet A1 to AN, and G bar I prime is the conversion of that to the prime alphabet. Now, I know this is a bit cumbersome of a definition. This is because Davis originally defines normal systems as a resulting system when applied to a different one. I believe he calls it a semi-2 system. Later on, he will refer to normal systems without the prime alphabet. I'm pretty sure they're equivalent, however. Now, this is again annoyingly cumbersome. Brainsia, books bizarre writing style. Thankfully, there is one nice thing about normal systems. Every recursively neural set is generally a binormal system with an alphabet of only 2 letters. Now, I'm not going to prove this largely because it's again fairly involved and we don't have infinite time. Now, consider words W over the alphabet 1B. You may be wondering why not the alphabet 01. The answer is simply that Davis used this in his book. Unlike so many other things in the book, it's a bit bizarre and unconventional. Now, we denote the length of W as O of W. We also define the place, P of W, to be W's index under classical graphical order among words of the same length. So, for example, P of 111 is 1, P of 1B1 is 3, P of 11B is 2, P of 1BB is 4, and so on and so forth. We also set the triple of W, T of W, to be O of W, P of W, to the O of W. This provides a nice encoding of words of W. From here on, we'll be working under a normal system, V with alphabet 1B, and rules GIP maps to P, G bar I. We define a new predicate. We say THV of XYZ or theorem of V if and only if there exists a word W such that V proves W and triple of W equals XYZ. Fairly straightforward. It's just a way of converting these theory into triples of numbers. For some problem number trickery, we can get the following. There is a diagonal predicate D1 of X, Y, Z, K, L, W, W prime, W prime prime, such that theory of V of X, Y, Z, if and only if there exists W, W prime, W prime prime, L, such that for K less than move to L, D1 of X, Y, Z, K, L, W, W prime, W prime prime. Now, again, I'm not going to prove this because I didn't particularly find that could prove to be very interesting. It was fairly long and involved some number manipulation in the background, and in the end wasn't all that enlightening. Moreover, it would take half an hour. Now, if that was starting to look a bit like Davis' normal form, you'd be correct. It's only a simple step to turn this into numbers being within the set of integers generated by V. We simply substitute in the necessary values for X, Y, and Z. Applying the new theorem 653, this turns the result into the following lemma. Given a recursively enumerable set, there is a diagonal predicate D2 of N, Z, K, L, W, W prime prime, such that one element of S, if and only if there exists a Z, a W, W prime prime, and an L such that for K less than or equal to L, D2 of N, Z, K, L, W, W prime, W prime prime. We can collapse the Z, W, W prime, W prime prime to a single integer V via use of a pairing function. Davis repeatedly applies a pairing from N down through, but pick your favorite system. It'll all turn out the same. Now, moving V and L together is a bit harder because L appears in the quantifier for K. In order to do it properly, we need a particular pairing function which Davis developed. Namely, it's a pairing function which he denotes as J of xy, with right inverse K and left inverse L. It has the nice property that L of y is less than or equal to y. Consequently, we can collapse V and L to a single variable y, and the entire thing becomes there exists a y such that for all K less than or equal to y, P of n by K, where P is a Diophantine predicate equivalent to there exists a VL such that D3 of n VKL or K with NL and y equals J of VL. So in other words, we trace all the way up to L of y and then ignore anything above it. Thus we have Davis normal form. Now, Davis normal form is interesting. However, it's not quite what we want. The for sign really makes it hard to deal with. Ideally, we'd like to show its Diophantine, but we're going to settle with showing that it's exponentially Diophantine. This process involves three large lemmas. The first lemma that we're going to prove deals with binomial coefficients. It specifically states that the relation x over y equals p over q choose k, and p greater than qk is exponentially Diophantine. Here x, y, p, and q, and k are integers, and we're looking at the quote-unquote generalized binomial coefficient. To prove this, we'll begin by setting alpha equal to p over q and defining s sub k of a equal to the sum from j equals 0 to k of alpha choose j times a to the quantity 2k minus 2j plus 1. Quite a mouthful, I must say. It's easy to see that for some theta between 0 and 1, a to the quantity 2k plus 1 times the quantity 1 plus a to the minus 2 quantity to the alpha equals sk of a plus theta alpha to the k plus 1 a to the minus 1 to alpha minus 1. If I recall, this was Taylor's expansion with Lagrange form or something like that. But we want to choose a such that sk of a is c for the greatest integer less than or equal to this number we just described. We also want the corresponding thing to hold for sk minus 1 of a. With some clever manipulation, we see that a equals 2 to the p, p to the k plus 1, q to the k, k factorial, is a desired value. Now, by clever manipulation, I mean rote numbers here, bit obscure stuff, and rather long to write out, so you'll have to take my word for it here. Now, we see Also that with this A, U equals SK of A, if and only if A to the 2P U to the Q less than or equal to 8 to the quantity 2K plus 1 times Q, all times the quantity A squared plus 1 to the P, which is less than A to the 2P U plus 1 to the Q. In other words, SK of A is directly as a result, since P over Q choose K equals A to the minus 1 SKA minus A SK minus 1A, the entire relation is directly as we had hoped. Now, to be a tad more, we've only shown that SK of A is directly. We haven't properly shown it for SK minus 1. But the corresponding result holds in a very clear story. Now, if lemma 1 seemed to be a bit unrelated to Davis normal form being eventually directed, that's because lemma 1 really serves no purpose than to prove lemma 2. In fact, lemma 2 is such an immediate consequence that I, to this day, do not understand why it's not called corollary 1. Regardless, lemma 2 states that the relation y equals the product of all little k less than or equal to big K of A plus B little k is exponentially directed. Proving this is very simple. Product of k less than or equal to big K of A plus BK equals A over B plus big K, choose big K, A times B to the big K, K factorial. Very simple, very quick. Unfortunately, the last lemma, lemma 3, is anything but quick and simple. It states this massive, horrible, terrible, god-awful, never want to read it, but I have to, result. Let f and g be polynomials with g of x, y greater than or equal to y, and for k, z, in 1 through cm less than or equal to y, absolute value of f of x, y, k, z, is less than or equal to g of x, y. Then for all k less than or equal to y, there exists a z less than or equal to y, such that f of x, y, k, z equals 0, if and only if there exists a c, here a t, and an a, such that t equals g of x, y factorial, and 1 plus ct equals the product of all k less than or equal to y of 1 plus kt, and 1 plus ct divides f of x, y, ca, and for I less than or equal to m, 1 plus ct divides the product of all j less than or equal to y of ai minus j. Now, proceeding onwards, I'll simply say that this states that Davis normal form, if and only if, terrible result. To prove lemma 3, let's start with the reverse direction. We're assuming as a terrible result that we will never have to pronounce again is true. Then we'll set k less than or equal to y, pk to be a prime dividing 1 plus kt, and cky equal to the remainder of ai under pk. With some basic number theory, this becomes a series of bounds. Y less than or equal to zki less than or equal to y less than or equal to g of xy less than pk. Continuing, we get c equivalent to k mod pk, and thus f of x, y, k, z, k, runs with z, k, m, equivalent to f of x, y, c, a, 1 through a, m, equivalent to 0, mod pk. Now, thanks to those bounds, this becomes f of x, y, k, z, k, 1 through z, k, m, equal to 0. Since k and zk are also to y, we have the Davis normal form side as desired. Now, let's do the forward direction and assume the Davis normal form holds. Then T and C are already uniquely determined. It's easy to trust that all k and j are socially indistinct. GCD of 1 plus kt and 1 plus jt equals 1. It also follows that we can find an AI equivalent to zki mod 1 plus kt. Thus, we have the previous equivalent f of x, y, k, z, k, 1 through z, k, m, equivalent to f of x, y, c, a, 1 through a, m, equivalent to 0. This time it's mod 1 plus kt. Since there's restrictions and with additional number theory, we get 1 plus ct equals the product of chaos will be y 1 plus kt. Actually, we don't need identity in that one apart. That's by definition. But this value divides f of x, y, c, a1 through am, and the product of all j lesser to y of ai minus j. Combined, these all make up that terrible result as we had hoped. Now, if we look at the horrible side of Lemmas 3, it's almost entirely exponentially developing. There's really only one part that we can't verify right away. That's the 1 plus ct divides the product over j lesser to k of ai minus j. If we can show that's exponentially developing, we're good. We'll have shown that Davis normal form is as well. Luckily, showing this party is fairly easy. We see that the relation holds if and only if ai lesser to y, or there exists a u such that ai greater than y and 1 plus ct equal any times u equals the product of j lesser to y of ai minus y minus 1 plus j. Bit cumbersome, but it works. And with this in mind, we see that Davis normal form is equivalent to an exponentially developing predicate, and thus is itself exponentially developing. Putting everything together, this finally yields DPR's main result. Every recursively enumerable set is exponentially developing. Now, if you've stayed up for this entire portion, or rather have stayed awake up till now, congratulations, we are halfway there. Without further ado, let's go on to Metasavage's results. Let's first describe the original proof in a non-technical manner. The total solution to Hilbert's 10th problem uses a theorem from Robinson, the same one from the previous result. And we say the theorem without proof. Again, I would like to, but we don't have infinite time. It states that if there is a relation 5uv such that 5uv implies v less than u to u. Now, I should note the original states u to the u to the u to the u and so on, n times for some n. but we only need n equals 1 here. But if it satisfies that, and also satisfies that for no n does 5uv imply v less than u to the n. So in other words, phi grows at a rate faster than polynomial, and levels in the double exponential. If such a phi exists, then z equals x to the y can be defined in terms of addition, multiplication, and phi. The Robinson's hypothesis is that there is a Diophantine such phi. It follows that if this is true, exponentiation is Diophantine, and consequently, of course, that would imply exponential Diophantine is the same as Diophantine. Now, Madiasevich, who I apologize, by the way, I just realized I've been mispronouncing his name for the entire time. It's Yasevich, not Sevich, but either way, he resolved this and proved the Robinson conjecture. His theorem stated that if f of n is the nth Fibonacci number, then n equals f sub 2m is Diophantine. As a result, if we write 5u v equals f of 2u, and u greater than or equal to 2, we've got the desired result. Thus, combining all this together, we get that since exponentiation is Diophantine, every recursively enumerable set is Diophantine. Unfortunately, Yana Govoyopolsky, I don't speak Russian. Madiasevich, of course, published all of his work in Russian. To the this language barrier, we're going to follow a different proof. This one was written by Davis in the 1973 survey on Hilbert's 10th. Now, there may be some confusion because this paper is actually well written in a way that makes sense, but this is the same Davis as from before. His proof is a lot more direct in that it actually shows directly that exponentiation is Diophantine. The methods it uses, however, are more or less the same as Madiasevich develops. The proof begins with so-called 24 easy lemmas. Now, when he says easy, they really are easy. Many of them we will state without proof, or with just a single sentence sketch. These lemmas all revolve around Powell's equation, which reads x squared minus the quantity a squared minus 1 times y squared equals 1 for x, y greater than or equal to 0 and a greater than 1. Usually we'll be interested in integral solutions. For convenience, we'll write d as a squared minus 1. The first two results are very easy to see. Lemma 1 states that if x and y satisfy Powell, and 1 less than x plus y root d less than a plus root d, then x and y aren't integers. In other words, if x plus y root d falls in this range, there's no integral solution. Lemma 2 similarly states that if x, y, and x prime y prime integral satisfy Powell, then x prime prime plus y prime prime root d equal to x plus y root d 20 times x prime and plus y prime root d. Then these x prime prime and y prime prime satisfy Powell as well. With this in mind, we define a set of solutions to Pell for n row equal to 0 and a row to 1, set xn plus yn root d equal to a plus root d equal to the n. Now, if you're wondering why we have to specify a root and 1, that's because in the original paper, xn and yn are functions of a, not solutions. This is a notation that Hilbert uses sparingly, so we simplify it here, as he himself does usually. Correctness, in fact, is very easy to see. xn and yn satisfy Pell by induction and lemma 2. Rather surprisingly, these xn's and yns characterize all non-negative solutions to Pell. This is lemma 4. If x and y grow down to 0, satisfy Pell, then for some n, xy equals xn yn. The proof of this is very straightforward. We can bound them because x plus y root d is root of 1 and a plus root d is root of 1. We get this inequality. If equality holds, we're done. If it doesn't hold, then multiply by xn minus yn root d, and we get the bound as shown in lemma 1. Thus, equality must hold. Now, with this algebra, we have lemmas 5 to 8. They're all very simple, more or less bash problems. You can solve them very quickly, so we'll state them without proof. Lemma 5 states that x sub m plus or minus n equals xm xn plus or minus d by n ym, and correspondingly ym plus or minus n equals xn ym plus or minus xm ym. Lemma 6 is just that, restricted to n equals 1 and simplified. Xm plus or minus 1 equals a xm plus or minus d by m, and ym plus or minus 1 equals a ym plus or minus xm. Lemma 7 is even simpler. It states that xn and yn are relatively prime, and lemma 8 states that yn divides yn k positive. The next two lemmas aren't much harder, but we will sketch some proofs, simply because they're a tiny bit less obvious. Lemma 9 inverts lemma 8 and shows that it's in fact if and only if yn divides by 2, if and only if n divides 2. To prove this, we use only the reverse direction. The forward direction. Let t equal n0 plus r, 0 less than r less than n. By lemma 7 and 8, yn divides by r, but by lemma 6, for example, by r less than yn. Lemma 10 states thatynk is equivalent to k, x sub n to the k minus 1, yn, mod yn cubed. Proof of this is just applied by a real equation to a plus root d to the nk. The next three lemmas continue to have one-line proofs. Lemma 11 states that yn squared divides yn by n. Proving this, I believe, is just lemma 9 or 10. Lemma 12 states that if yn squared divides yt, then yn divides t. To determine that the proof involves lemma 7, 9, and 10. Finally, lemma 13 states that xn plus 1 equals 2axn minus xn minus 1, and yn plus 1 equals 2a yn minus yn plus 1. Proving this, you basically take lemma 6, you turn it into system of linear equations, and reduce. Now, at this point, you're probably a bit confused. We're halfway through all the lemmas, and this seems to be fairly random. Well, that is the beauty of this method. They will all seem random until they get tied together at the end. Lemmas 14, 15, and 16 all use basically the same one-line proof. It's induction and modular arithmetic. Lemma 14 states that yn is equivalent to n mod a minus 1. Lemma 15 states that if a is equivalent to b mod c, then xn a equivalent to xn b, and yn a equivalent to yn b mod c. Now, this is that dependence of xn that I mentioned earlier. If we're replacing, or rather fixing the value of a in Paris equation, it's, again, used very rarely, this notation. Lemma 16 simply states that yn and n have the same parity. Lemmas 17, 18, and 19 are much the same in that they have equally short proofs. 17 states that xn minus yn times the quantity a minus y is equivalent to mod to the n, mod 2a y minus y squared minus 1. 18 provides a bound of yn, and it shows it's between yn plus 1 and n. And 19 provides a bound on xn, shows it's between xn plus 1 and a to the n. It also shows it's less than or equal to 2a to the n. Now, at this point I'm feeling bored. It seems like we're just laundry listing a bunch of facts about Paris equations. Kind of like an undergraduate's very first attempts at trying to discover something. But I promise you, it pays off well. The next three lemmas all deal with periodicity results. Lemma 20 states that x sub 2n plus or minus j is equivalent to negative x sub j mod xn. 21 takes this a step further, states that x sub 4n plus or minus j is equivalent to xj mod xn. And lemma 22 states that if xi is equivalent to xj mod n, and I less than to j less than to 2n, and n greater than 0, then I equals j, or we have one exception case. Lemma 22 is really not obvious, and it has a long proof, so we'll go out for it. Unfortunately, when I typed up Lemma 22's proof, it was not a pleasant experience. By that I mean the proof was a bit dense, and it, as a result, was spread out over an annoyingly large number of slides. This made it a very unpleasant viewing experience. Of course, the only thing to blame was Beamer, and absolutely not my ability to adapt the proof to slides. Either way, to get around this, I've done the unthinkable and scanned in the paper's proof as an image file and put it in Writer. Now, it doesn't look as good, and I do apologize for that, but it's at least not 10 slides. Now, we'll begin by assuming xn is odd, and writing q equal to half of it. Then the integers from minus q to q minus 1 all different mod xn. Number 119, xn to xn minus 1, or monotone increasing sequence beginning with 1. Applying limit 2.6, we get xn minus 1, is also equal to xn over a, which is also equal to half xn. Thus, xn minus 1 and the entire sequence is bounded by q. Also by limit 20, these numbers are congruent to negative xn minus 1 through negative x0, itself equal to 1. Minus 1. Thus, x0 through x2n are all different mod xn, given the result. Now let's suppose xn is even, and beginning as before. The result will prove in the same manner, unless we have one edge case, xn minus 1 equal to 2, which is, again, xn over 2, in which case xn plus 1 is equivalent to minus 2 mod xn, in which case I equals n minus 1, j equals n plus 1, contradicts your result. By limit 2.6, however, this will only happen if a equals 2 and yn minus 1 equals 0, well, i.e. n equals 1. Thus we get our terrible edge case, which already corresponds. The last two lemmas are of a similar form, however they are much more easily proven. 23 states that if xi is equivalent to xj mod xn, and 0 less than r so equal to n greater than 0, and 0 less than or equal to j less than 4n, then either I equals j, or j equal to 4n minus I. And lemma 24, a bit shorter, begins the same way. If xi is equivalent to xj mod xn, 0 less than r so equal to n, then j is equivalent to plus or minus I mod 4n. With this, we have concluded the 24 easy lemmas and are ready to prove the final piece. With the lemmas out of the way, we can now arrive at the heart of the Davis survey proof. It involves this Diophantine system of 8 equations: x squared minus quantity a squared minus 1, quantity times y squared equals 1, u squared minus quantity a squared minus 1, quantity v squared equals 1, s squared minus quantity b squared minus 1, t squared equals 1, v equals y squared, b equals 1 plus 4py equals a plus qu, s equals x plus cu, t equals k plus 4, quantity d minus 1 times y, and y equal to k plus e minus 1. Seems fairly random, right? Well, not quite. The first three, you're looking at like Powell's equation. But, that being said, ignoring that, it still seems pretty off balance. But it isn't, because, in fact, as hard as it may be to believe, this system has a solution if and only if x equals x k of a. Now, I'm going to warn you in advance, from here on until the end of this presentation, all the proofs will be done in the same manner as on the 22s. I've scanned in the proof and put the images here. It's for the same reason. These are long proofs, and going through them, one sentence at a time, is really not a fun experience. It may not look as nice, but trust me, it is better. Now, without further ado, let's prove this. Let's first assume there is a solution. Then, by 5, we have b greater than a greater than 1. 1, 2, and 3 imply beside it. 2.4 that I, j, and n are greater than 0, such that x equals x if a, y equals y if a, u equals x n if a, v equals y n if a, s equals x j b, and t equals y j b. Now I know this is just that the x, n's, and y's in numerator are the solutions. Now by 4, y is also equal to v, so I is also equal to n. Now 5 and 6 is your congruencies. B is equivalent to a mod x n of a, and sj at b is equivalent to xi of a, and mod x n of a. Thus by lemma 2.1 and 5, we also get xjb is equivalent to xj of a mod x n of a. Thus xi of a is equivalent to xj of a mod x n of a. And thus by lemma 2.24, j is equivalent to plus or minus I mod 4n. Now, equation 4 thus yields that yi of a squared divides yn of a. Thus by lemma 12, yi of a divides n. And the first equation combined with this yields that j is equivalent to plus or minus I mod 4 yi of a. Thus, by equation 5, b is equivalent to 1 mod 4 yi of a. Thus, by lemma 14, jb is equivalent to j mod 4 y of a. Thus, by equation 7, jb is equivalent to k mod 4 yi of a. Combine these all together gives k is equivalent to plus or minus I mod 4 y of a. Equation 8 yields that k is also equal to yi of a, and thus by lemma 18, I is also equal to y of a. Now, since the n moves from minus 2y plus 1 to 2y, the residue is mod 4y, which is equal to 4y of a. And we have that these inequalities force that k equals I. Thus, x equals xi of a equals xk of a. Now, to prove the reverse direction, it's a tiny bit more dense, but not shorter. To prove said direction, let x equal xk of a and y equals yk of a. Then one holds, that is the first equation holds. Letting m equal to 2k by k of a, and then u equal xm of a, v equals ym of a. Then we get equation 2. M is 9 and 11, and it yields that y squared divides v. Hence we can choose an r satisfying 4. M is 16, v is even, and thus u is odd. M is 7, they are relatively prime, hence u is relatively prime, and to b times 4y. Right, there's a paper justification here, which are separable. Thus we can find the b naught such that b naught is equivalent to 1 mod 4y, b naught is equivalent to a mod u. Obviously, b naught plus 4j will satisfy these congruences. Thus we can get a b, p, and q satisfying the fifth equation. 3 satisfy both S and T as you would expect by now. Since B is greater than S is greater than X. Thus, 15 and equation 5, S is equivalent to X mod U. Thus we can choose C satisfy in 6. 18 and 14, we get T is equivalent to K mod B minus 1. And thus using for I T is equivalent to K mod 4. Thus we can satisfy 7 and choose D. Thus by 18, we can satisfy equation 8 by saying E equal to Y minus K plus 1. To finish up, we need one last drama. It's very easy to prove, so we say it without proof. Also, at this point, we'll really be into a lot of time. Problem 3.4 says that if A is greater than Y to K, then 2ay minus y squared minus 1 is greater than y to the K. Now, with this, we can add 4 new equations to the system. The first is that the quantity x minus y times quantity a minus y and quantity minus m and quantity squared equals quantity f minus 1 quantity squared times the quantity 2an minus n squared minus 1 quantity squared. Second is that m plus 3 equals 2an minus n squared minus 1. The third is that w equals m plus h equals k plus l. And the fourth is that a squared minus the quantity w squared minus 1 times the quantity w minus 1 squared times z squared equals 1. Now, these probably seem a bit arbitrary, but the previous ones did also look at what they proved. This form will in fact yield the necessary restrictions to make the new system define exponentiation. This extension means that there's only a solution if m equals n to the k. So, are you guys ready to prove this? This is our last proof. Exciting, isn't it? Well, unless you fell to sleep, in which case I regret to inform you that you'll be woken up soon. Either way, let's suppose the first 12 hold. Then by 11, w is greater than 1. Thus w minus 1 times z is greater than 0. Thus by, as a 12th one, a is greater than 1. Applied to 3.1, we get that x is xk of a, and y is yk of a. Thus by 9 and 17, m is equivalent to n to the k, by 2an minus n squared minus 1. 11 yields kn less than w. Thus, using 12 and limit 2.4, for some j, a equals xj of w minus 1, and times z equals yj of w. Thus, by 14, j is equivalent to 0 by w minus 1, and thus j is greater than or equal to w minus 1. Thus, by 19, we abandon w to the w minus 1. Namely, a is greater than or equal to it, and n to the k is less than it. Thus, thus by 10, m is less than 2an minus n squared minus 1, and by limit plus 3.4, n to the k is less than 2an minus n squared minus 1. Since m and n to the k are congruent and both less than the modulus, they must be equal. Now, suppose that M equals n to the k, then we need solutions for the equations. Choose n and w greater than n greater than k, and set a equal x sub w minus 1 of w, so that a greater than 1. By lemma 14, y w minus 1 of w is equivalent to 0, and w minus 1. Thus we can write y w minus 1 of w equals c times w minus 1. Thus we satisfy 12. Now, 11 can be satisfied with h equals w minus n and l equals w minus k. As before, a is greater than n to the k, and thus by lemma 3.4, m equals n to the k, it is less than 2an minus n to the minus 1. Thus we've satisfied 10. Setting x equals x k by y equals y k by lemma 17, it allows us to choose f such that x minus y times quantity a minus n and quantity minus m equals plus or minus f quantity f minus 1 times quantity 2an minus n to the minus 1. Thus now I'm satisfied. Solutions for the first stage, followed by theorem 3.1. And that's it, guys. We've proven theorem 3.5 and have proven that exponentiation is diagonal. It now follows immediately the result we've been looking for, that since exponentiation is diagonal, every recursively enumerable set is diagonal. Thus, we trivially get no algorithm exists satisfying Hilbert's 10th problem. We've done it. We have proven it. Congratulations to everyone who followed this and stayed awake for it. Thank you, and do you have any questions?